let's go on to line integrals. And let's write down this definition. 16.1, if we're in the current book. A curve C. So we're talking about just some curve, right? Normally, up until now, we've been looking at curves in space. We can define them by like f of x or g of x, and that's what you're picturing. But now it's in space, so we're looking at like the r of t concept. All right, so a curve C is defined by r of t, and that's the one in space. Okay, and we're defining smooth as well right here, by the way. So give me a second here. Okay, so this curve r of t, x of ti plus y of tj plus z of tk is smooth. That's the other definition we're talking about. If each of those derivatives or partials, well, they're derivatives because it's single variable t, are continuous, so not only exist, it implies they exist. Not only that, but they're continuous on AB and not all zero, so that simultaneously zero on AB. A curve C is called, so that's the definition of smooth. That is, they're differentiable, each of those, dx, dt, dy, dt, dz, dt, and not all zero at the same time. So that's what we mean by it. Okay, the curve is called piecewise smooth if you can basically cut it up and it's smooth on those individual intervals. So it's piecewise smooth if AB can be partitioned into a finite number of subintervals on which C is smooth. Okay, and I'll have a picture of that. So write that out and draw this picture. Erase some of that cover up. We'll try to not cover up stuff like that all the time, but definitions take a while to write out sometimes, so you can try to do that on your own. Okay, let's look at a line integral and what this means. So when you define a line integral, you're going to use a piecewise smooth curve defined by r. I mean, that's basically what's going on here. Right, so a line integral is this, and we're going to define it in terms of r or in terms of f of x, y, z. Okay, so it looks like this. You have the integral over c, right? So something defines c of f of x, y, z. Move that up a little bit. ds is equal to the limit as the norm of the partition approaches zero of the sum as I goes from 1 to n of f of x sub I, y sub I, z sub I, delta s sub I. And so what you're basically doing is taking that curve and you're going to break it up into pieces. So if you break up the curve into pieces and just don't have that function in there, then you get the length of that curve. So basically, if f is equal to 1, we get length. Okay, so that's what's happening in that case. So what we're really concerned with too, or not concerned, what we really need to look at then is what's this ds part? Like this doesn't help us at all. This integral is like, great, that's fun to work with, but we need to know the ds and all that. So ds really means the magnitude of r prime of t dt. And so the magnitude of r prime is the sum of the square roots of the derivatives. So it's the sum of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. Just move that over there for now. dt. Okay. And then, as I mentioned a second ago, if this f is 1, then you really, all this means, that's a formula we would have derived a while ago. That just means you're adding up the lengths, and that is derived using like mean value theorems and stuff like that. I forget where we were with that one, but you can look back. So this next form is what we would call the evaluation formula, and that's really what you need or interested in. So evaluation formula. So if you have the integral over c of f of x yz ds, that's equal to the integral from a to b of f of x of t, y of t, z of t times the square root of all of that above. So it's all of this above. I'm just going to copy it. dt. So you can replace that the square root. That's really, this is how you'd write it down or something. It's magnitude of r prime of t. That's what you need to know. dt. Okay, so that's your ds right there. So, and remember that r prime is velocity, right? So if you do r prime, that's really just v of t. So you know that r equals v, r prime is equal to v is the velocity there. All right, let's look at an example using that formula. So evaluate the integral over c of 2x squared y ds. And then now we got to tell you what c is. Where c is a portion of the parabola y equal to x squared from the point negative 1, 1 to 2, 4. So this is more or less a not a vector valued function, so we need to put it in that form essentially. Note that the points have to be on the curve, so they have to satisfy the y equals x squared. So we have f of x is x squared, like that. And we want to define the curve parametrically. So define the curve parametrically. So we will let x equal t, then y is equal to t squared for t in, and then it just has to be -1 to 2. So, oops, it's got to be -1 to 2 because that's what x is. So that's like your AB. Okay. So now we can do the substitution. So we substitute for x and y in terms of t. So f of xy is equal to 2x squared y, which is 2. And then what is x? X is t, so it's 2t squared. And then what is y? Well, y is t squared, as it's defined above. So it's t squared. And so that equals 2t to the 4th. Okay, so that's when you plug in up here, that's what it's referring to. It's those functions in terms of x, in terms of t. So it's x in terms of t, y in terms of t, z in terms of t. Now this is just 2d because the way it was given. All right. So now let's calculate ds. So that's always going to be your next step. So ds is the again, we're leaving off that. So it's just these two as a sum. So the x is just t, so that's just 1. And then y will be just, where is it? It was here, so that'll be just 2t quantity squared. So you get 4t squared. So ds is equal to the square root of 1 squared plus 2t squared dt. So we have the integral over c of 2x squared y ds equal to integral -1 to 2, and then 2x squared y is 2t to the 4th times the square root of, and I'm going to have to bring this back down here. Keep doing that. All right, so where do we go? This is 1 plus 4t squared dt. Okay, so keep in mind again that this is your ds, and then this is your function, and everything now is in terms of t. So you have to get it in terms of just something you can integrate. The ds, like, what does that mean until you actually evaluate something? Okay, then you evaluate that. It's not simple, but you have, I think you can do it in terms of u substitution and then break this up. Because if you do u is 1 plus 4t, you get a t outside, but this is t to the 4th. I don't have this worked out, so try to work it out. This is approximately 45.391. So I don't have anything exact. At this stage, a lot of it's going to be just setup and not evaluate, like on an exam, even a take home or online, and in class, of course. Homework, you want to work it out. Don't always just use a computer algebra system to get your solution. You probably know that by now in this class. But in this case, that's what I have to speed things up. Okay, a couple things. So note, if you wanted to describe this, if you can write the line integral like this. So if you have some sort of curve and say it's like a wire, right? It's defined somehow. If you write it as delta x y z is equal to density per unit length I just erased that. That was weird. If it's density per unit length, then you can. So if delta is density per unit length, then if you do this line integral, you can get mass of the wire. So the mass equal the integral over c, which is the curve, and then this is your delta x y z ds. So that would be like mass of whatever that is. So if the density happens to change of something like that, some wire, then that function f of x, y, z can be expressed in terms of density per unit length. There might be a couple like that. Okay, that's pretty much 16.1. The easier cases, I believe, are when the function is given in terms of, the c is given in terms of r. If that's the case, then you just plug it in, and you substitute in for your x of t, y of t, z of t. That'll be given because those will be determined in terms of x, y, and z anyway. So check those out too. Okay. Next, we move on to line integrals and vector fields.